Finding the right abstraction for a complex API like Vulkan is hard. If you ever worked with Vulkan, you know exactly what I mean. Vulkan gives you incredible control and performance, but that control comes at the cost of complexity. You have to think about memory, synchronization, pipelines, render passes, descriptor sets, swap chains. In this video, I want to walk you through how I designed my own graphics abstraction layer over Vulkan, OpenGL, and OpenGL. The API is a pure C interface that avoids any object orientation or inheritance. I found that these concepts only complicate the design. A valid question to ask is, why should you even bother with an abstraction layer at all? First, I want something that's easy to work with. I don't want every part of my engine to care about Vulkan specific details, because that is very error prone and time consuming. Second, I want to support multiple graphic APIs. In my engine, I currently support Vulkan and OpenGL. More specifically, I support OpenGL ES to run on older phones that don't have Vulkan available. To support multiple graphic APIs, the graphics device dispatches to different backends. In the graphic device alloc function, I try to initialize one backend after another. If the initialization succeeds for a backend, this backend gets chosen. The graphic backends themselves populate a struct of function pointers. This is similar to a read table in object-oriented terms. All rendering code goes through this table. The core pattern I've settled for the API is that every GPU resource is represented as a handle. A resource can be an image, a buffer, a shader, a frame buffer, and for every resource there is an alloc function, a release function, and a create info struct that describes how the resource should be created. So instead of dealing with objects and pointers, you only have to deal with handles. The benefit of handles is that it's easy to check if they're still valid. This design gives the implementation side a lot of freedom and doesn't force you into a specific pattern like object orientation. On top of allocation and release, each resource only exposes a very small set of operations. For example, buffers have map and unmap functions, images have functions to query their size. I try really hard to only expose what I actually need. I think this is good API design principle in general. If the engine doesn't need it, it shouldn't be in the public interface. In addition to resource functions, there's a second category of API calls, command functions. These are the G_CMD functions, and they are used to execute work on the GPU. The command function allow you to begin and end render passes, bind pipelines, buffers, and shader materials, and finally issue draw calls. One interesting decision I made here is to expose Vulkan's push constants. If you're not familiar with push constants, they are special uniforms that are very cheap to update. They are typically used for data that changes at very high frequency, like for example per draw call. In OpenGL they don't exist directly, but map nicely to regular uniforms. Someone may notice that there is no command buffer resource. I decided to hide command buffers internally as my engine doesn't profit from them being exposed. The G_CMD functions internally work on a command buffer, but the user doesn't need to know about that. Let's quickly go over the available resources. Textures, buffers, and shaders are pretty self-explanatory. One interesting thing here is that I only expose a buffer resource. On the create info struct, it can be specified which type of buffer should be created, like for example index buffer, vertex buffer, shader storage buffers. The more interesting resources are pipelines, render passes, and shader materials. Pipelines and render passes map one-to-one to Vulkan objects. Shader materials are my abstraction for Vulkan descriptor sets. A pipeline contains all the required states to draw an object. For example, the shader, the blend state, the rasterization state. Render passes encapsulate the required frame buffers for drawing, for example, which surfaces to draw on. In Vulkan, they also ensure synchronizations of the memory between the passes. Shader materials specify the resources needed by the shader to draw. For example, if the shader expects a texture, the shader material would contain the actual texture handle. There are actually two types of shader materials. There's a frame shader material and a regular shader material. Frame shader materials can be created every frame and will be freed automatically at the end of the frame. This is very helpful to bound resources that change every frame. This is what I use for my sprite renderer. Pipelines, render passes, and shader materials do not exist in OpenGL, therefore I emulate them and use them to pass the right information to OpenGL when executing draw calls. I want to talk about two things in a bit more detail in that video. First, the shader workflow, and then the shader materials, as I think this could be interesting. The problem with writing shaders is that every graphic API expects its shaders to be written in a different language. For example, Vulkan expects its shaders to be written in SPIR-V. OpenGL expects GLSL. It gets even worse if you bring in APIs like Direct3D and Metal, which come with their completely own shader languages. I want to write my shaders only once. I write them in Vulkan GLSL and then cross-compile them for other APIs. For this, I leveraged the library SPIR-V Cross and wrote my own shader compiler around it. As part of the shader compilation, I also generate reflection data, which I store in a separate file. For those of you that don't know what SPIR-V Cross is, it's a library that allows you to compile shaders for different shader languages from a shader in SPIR-V format. SPIR-V is an intermediate language for shaders, and it's the shader language that Vulkan expects. The generated reflection data is especially helpful for Vulkan to create a pipeline layout and a descriptor set layout automatically. This avoids a whole class of errors and a lot of boilerplate code. I found descriptor set handling one of the more challenging aspects of Vulkan. There are many different ways to deal with them, and I could probably fill a whole video just talking about them. But the gist of it is that I use the reflection data that I generated to create a descriptor set automatically. A quick word about synchronization. One of the main differences between Vulkan and any other graphic API, besides DirectX 12, is that Vulkan requires you to synchronize the memory manually. This can be very challenging. I expose as part of the command interface also synchronization functions that are inserted manually if needed. In OpenGL, these are mostly no-ops. To finish this video, I want you to walk through how it looks like using the API during a frame in my game. We begin the frame by calling gBeginFrame and obtain the swap chain index. Next, we begin a new render pass. The labels help to debug in a frame debugger like RenderDoc. Then the canvas performs its rendering work. We update the vertex buffer and set the pipeline required for drawing. Next, we bind the vertex buffer, set the viewport in scissor, allocate a frame shader material, set the push constants, and then execute a draw call. After all drawing is done, we end the render pass. At the end, the recorded draw commands get submitted to the GPU with gsubmitFrame. So yeah, that's a quick overview how I approach the graphic API abstraction in my engine. It's definitely not perfect, but it works pretty well for me. After I had the Vulkan implementation in place, it took me only 2 evenings to add the OpenGL implementation with almost zero changes to the public API surface. I hope this gives you a few useful ideas. Let me know in the comments if there is interest in covering aspects of this in more detail.